today's lesson, we're going to look a little bit more at our identities, and we're going to look at some of the simplification of our identities, or how we use them to simplify trigonometric expressions. And also we're going to look at how we perform operations, addition, subtraction, and multiplication with our trigonometric identities. So let's start out by reviewing some of the identities that we've already learned. These are our basic or fundamental. We have our reciprocal identities. The cosecant of theta is equal to 1 over sine. The secant of theta is equal to 1 over cosine. And the cotangent of theta is equal to 1 over tangent. Another way of reading this is cotangent theta equals the reciprocal of tangent. And the cosecant of theta is equal to the reciprocal of the sine. And we know that to make reciprocals, we put 1 over that value. Now, you're going to have a lot of memorization to do, and so sometimes our brain only holds so much. So of your reciprocal identities, if you learn these three, then you should know these three. If you know that the sine is the reciprocal of the cosecant, then you should know that the cosecant's the reciprocal of the sine. It just kind of works backwards. It's like when you learned your multiplication. Once you learned that 2 times 3 was 6, then it wasn't hard to learn that 3 times 2 is 6. So I would recommend, you're learning these three, and then you would know these three. We also have our ratio identities, and our ratio identities deal with tangent and cotangent. The tangent of theta is equal to the sine over cosine, and the cotangent is equal to the cosine over the sine. Again, if you know the tangent, then you should know the cotangent because they're reciprocals. And then the last ones are called our Pythagorean identities. And again, if you would learn these three main ones, the other ones you can get by just doing some simple algebra. If you know that the sine squared of theta plus cosine squared of theta equals 1, then if you need to, you can solve for sine, and that would give you then that if you want to solve this for sine, then that would give you that the sine squared of theta is equal to 1 minus cosine squared theta. Or if you needed to know what cosine was, well, you can subtract sine squared, so that you would also know then that cosine squared theta is equal to 1 minus sine squared. So I don't know that it's necessary to remember these, because you can get to them very quickly from these. So again, I would say that you memorize the main ones. Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And then cotangent squared plus 1 equals cosecant squared. And then to find the other ones that go along with these, the variations of these, it's just a matter of solving. So tangent squared equals secant squared minus 1. Now what we're going to do today is we're going to take other expressions, and using our identities then, we're going to we're going to do some simplification. And this is just some exercises to help you learn what you can do and how you would use your identities. You don't always do every one of these, but sometimes you will. Let's say we want to start with cotangent theta. Now, often we want to write our expressions in terms of sine and cosine. And so sometimes what you will do is you'll take an expression, and by using your identities, then you'll write it strictly in terms of sine and cosine. And so that's what we want to do here. We've got cotangent, and we want to write this in terms of only sine. Now, if we went back to our identities, we don't have an identity that deals with just cotangent and sine. Here we have a cotangent equals cosine over sine. So that might be something that we could use. Down here we have a cotangent squared equals cosecant squared, but we don't have anything that gets us directly cotangent and sine. Now, cosecant is the reciprocal of sine, so we might could use something along that line. So let's just start with that and see how it would work. We know that cotangent squared theta plus 1 equals cosecant squared theta. So if we solve this for cotangent, cotangent squared theta would equal cosecant squared theta minus 1. But we only want sine. Well, we know that cosecant squared is 1 over sine. And so cosecant theta is 1 over sine, so cosecant squared would be 1 over sine squared. Well, here we're going to have to do some computation or some operations, and we'll do a little bit more of this in just a little bit. But anytime you're trying to add or subtract fractions, you need a common denominator. Well, for these, our common denominator would be sine squared. So we have 1 over sine squared, and 1 is sine squared over sine squared. So this would be 1 minus sine squared over sine squared. So now we have it strictly in terms of sine, but what we have is cotangent squared. We need cotangent. So to solve for cotangent, we would take the square root of both sides. So we would have cotangent of theta equals plus or minus. Now over here, when we take the square root of this, we have to take the square root of the numerator, which we can't do, so we would write that as 1 minus sine squared theta over the square root of the denominator, and the square root of sine squared is sine. So now we have cotangent theta written in terms of just sine. Now there's often more than one way that you can do things, and that's one of the nice things about our trig and our identities is you do it the way that you see. Some of you may have said, well, I didn't see using that identity. What I saw was using the ratio identity. Well, let's just go through and do this using the ratio identity. And so if we did that, we have cotangent theta. I'm going to draw a line here because this is a whole separate problem. So cotangent theta equals cosine theta over sine theta. Now we only want sine, so we stop here and think, well, is there a way that we have that deals with cosine and sine? Well, we have a Pythagorean identity that says that cosine squared theta plus sine squared theta is 1. Well, we're wanting to write cosine in terms of sine, so we'll solve this for cosine. Cosine squared equals 1 minus sine squared. And then taking the square root of both sides, cosine theta equals plus or minus the square root of 1 minus sine squared theta. So now we can replace cosine with plus or minus the square root of 1 minus sine squared over sine theta. And if you'll notice, we got the exact same answer. We just approached it a whole different way using two different identities, but we still got to the same place. And that's one of the things that you need to recognize is there will be more than one way often. And you might say, well, this way was a lot easier. That's not always our objective. Our objective is to get there. And so if you saw by using a Pythagorean identity how to get there, then that's a good way. If you see how to use your ratio identity to get there, then that's a good way, because both of them got us there. All right, let's take another one, and let's do this one in terms of cosine only. So let's take our cosecant theta, and we want to write it strictly in terms of cosine. Well, we know that cosecant is 1 over sine. We don't have an identity that deals strictly with cosecant cosine. Now, we need to change sine to cosine. So again, we go back to that Pythagorean identity. Cosine squared plus sine squared is 1, and sine squared is equal to 1 minus cosine squared. You're going to see quickly why it's so important to have these fundamental identities memorized, because you're going to use them often. So sine theta is equal to plus or minus the square root of 1 minus cosine squared theta. So we have 1 over plus or minus the square root of 1 minus cosine theta. And the way you would use these is if you were given what the cosine of theta was, then you could substitute it in and deal with cosecant theta without having to go through your definitions. It's not that this is a better way than using the definitions. It's just a different way. So sometimes what you want to do is write an expression in terms of either sine or cosine or both. So let's look at one where we write it and we can leave it in terms of both sine and cosine. And a lot of times those are a little bit more involved. So we've got the expression secant theta times tangent theta. Now when we get through with this, we only want sines and cosines. And then we always want to simplify it down if we can. So let's stop and think what we know in terms of sine and cosine. We know that secant is the reciprocal of cosine. So we could write secant as 1 over cosine theta. Tangent, we have a Pythagorean identity, but we're wanting sine and cosine, and we have a ratio identity that says that tangent is equal to sine theta over cosine theta. So now we can do our multiplication, and we can have this as sine theta over cosine squared theta. So now we've written it in terms of just sine and cosine. Now some of you might say, well, we could go even further. We know that sine squared plus cosine squared, and you don't have to write this each time. I'm writing it so you'll know where I'm coming from. We know that sine squared plus cosine squared is 1, and we know that cosine squared is equal to 1 minus sine squared. So we could replace this cosine squared now with 1 minus sine squared, and we've got it written in terms of only sine, which might be a little simpler. But either one of these, but if their directions are write it in terms of sine and cosine, then this is acceptable and this is also acceptable. So but you're going through and you're substituting in these identities that we have worked hard to learn. Let's look at another example where we write it in terms of sine and cosine. Let's take the expression cotangent theta minus cosecant theta. Now we want these in terms of sine and cosine. So cotangent theta, and as you're doing these, you may have to look back every once in a while, but cotangent theta is cosine over sine. Hopefully you've gotten them memorized to where you don't have to look back each time, but can think of the identity. And that's the goal that you have, is to get this to where you can think, okay, cotangent is cosine over sine. Cosecant, well, our reciprocal identity says this is 1 over sine. Now we have two fractions that we're subtracting. To be able to subtract, we need a common denominator, which we have. So this would be cosine theta minus 1 over sine. It's a little bit simpler if you write it over one denominator. And now we've got this that's a little bit more complicated. And part of the reason is if you look at your calculator, you don't have a cotangent button or a cosecant button. If you're going to have to find those, you're going to have to deal with those as the reciprocal of the sine. And so that's another reason that a lot of times we like to take our expressions and write them in terms of sine and cosine, because then if we're needing to find values, those are the ones we can find a little bit easier. Okay, let's look at one more where we change it to terms of sine and cosine. We'll try to do one a little bit more involved. Secant theta minus tangent theta times sine theta. Okay, we want to go back sine and cosine. So we're going to think secant. Secant is the reciprocal of cosine. So we could write secant as 1 over cosine. Now tangent, there's a ratio identity. Tangent's equal to sine over cosine times sine. And if you want to put that as sine theta over 1, you can. If that makes your multiplication easier, you don't have to. So we have 1 over cosine minus sine squared over cosine. Okay, now we have a common denominator, so we can write this as 1 minus sine squared theta over cosine. Okay, anytime you see a 1 and a function squared, you might want to check your Pythagorean identities to see, well, is there something we could do? Well, if you think back to your Pythagorean identities, we have sine squared plus cosine squared equals 1. And so if we subtracted sine squared from both sides like we did here, cosine squared equals 1 minus sine squared. Well, notice that's what we have here in our numerator. And so we could actually replace that numerator with cosine squared. So we have cosine squared theta over cosine theta, which would be cosine theta. So we've taken this expression up here that looks fairly complicated, secant theta minus tangent theta times sine theta, and by just using our identities and addition and subtraction, we have simplified that down to just cosine theta. And this is one of our big uses for our identities, is it helps us do some simplification. And we want to look then at our basic operations with our trigonometric expressions and see that we will work with these the same as you worked with numbers, the same as you worked with radicals, the same as you worked with complex numbers. We learn a process, and then we use that process with our different expressions. So if we wanted to add or subtract, and so we're going to do some addition or subtraction. And let's take the expression 1 over sine theta minus 1 over cosine theta. Okay, we want to subtract these. Now back in subtraction, in addition, you learned with fractions that you have to have a common denominator. So that's what we're going to have to do here. And a few times when you start out with these and where you've got a trigonometric function instead of a number, you might need to stop and think about, well, what do I do? And you might just think, well, this is a problem the same as 1/5 minus 1/3. Well, here we would get a common denominator. Since both of those are prime, they didn't have any factors. Our common denominator would be 15, or 5 times 3. And then we would make an equivalent fraction. What do we have to multiply 5 by to make it 5 times 3? Well, 3, so that's what we would multiply our numerator by. Then we would go over here. What do we have to multiply 3 by to make it 5 times 3? Well, by 5, and so that's what we would multiply our numerator by to make us equivalent fractions. So we would have 3/15 minus 5/15, and that's the same as 3 minus 5/15, or negative 2/15. Well, when we come to our trigonometric expressions, we're going to do the same thing. We need a common denominator. These don't have any common factors, so our common denominator is going to be sine theta times cosine theta. Now, what do we multiply sine by to make it sine times cosine? Well, by cosine. So that's what we'll multiply our numerator by. Here our common denominator was sine theta times cosine theta. Well, we had to multiply cosine times sine to make it sine times cosine. So that's what we're going to multiply our numerator by, is by sine. So what we ended up with, and I'm just going to write it over one denominator, we ended up with cosine theta minus sine theta over sine times cosine. So you do your addition and subtraction exactly the same way. You're going to have to get you a common denominator, make equivalent fractions, and then do the computation. If we had this as our problem, 1 over cosine theta minus cosine theta. And if you stop to think, this would be something like 1/3 minus 3. Well, again, we have to get a common denominator. And our common denominator here is cosine theta, for cosine theta and 1. So this one's already over the common denominator. We don't need to do anything. We need a common denominator of cosine, so 1 times cosine is cosine. So we'll have to multiply our numerator by cosine theta. And we end up with 1 minus cosine squared theta over cosine. Now, our Pythagorean identity, I see a 1 and a cosine squared. I know sine squared plus cosine squared is 1. So sine squared would be 1 minus cosine squared. So we could simplify this down to sine squared over cosine theta. And so we've got it, we've done our subtraction. If we have one more, let's do an addition problem. So we've got cosine theta over sine theta plus sine theta over cosine theta. We need a common denominator. Well, it's going to be sine times cosine. So sine theta, cosine theta. So this one we had to multiply by cosine, so that's what we're going to have to multiply our numerator by, is by cosine theta. And you can see that right here, all I've done is multiply it by 1. There's my cosine over sine. I've multiplied it by 1, so I haven't changed any values. Common denominators, sine theta times cosine theta. So I had to multiply cosine theta times sine theta. So that's what I'll multiply my numerator by, is sine theta. And again, you can see that all I've done is multiply that one by 1. So that I've made equivalent fractions. So what I have then is cosine squared theta plus sine squared theta over sine times cosine. We always try to write this just over one denominator. And we did our addition. But I see a sine squared and a cosine squared, and I know that my Pythagorean identities tell me that cosine squared plus sine squared is 1. So I can replace that with a 1, and I've got my expression. I've done my addition. Okay, that's addition. And subtraction just get you common denominators, make you equivalent fractions, and then do the addition. You do try to simplify at the end. Let's look at some multiplication. And we're going to start off with one where we've got sine theta times 3 plus cosine theta. Now, as we do our multiplication, remember we use the distributive property, so we're going to multiply sine times 3 and have 3 sine theta plus sine times cosine. You just distribute just like we would with numbers, just like we did with variables, with radicals. We just go through and do our multiplication. If we wanted to do multiplying 1 plus tangent theta times 1 minus tangent theta. Now, this should look like multiplying two binomials. You know, x plus y times x minus y. And so you can multiply those binomials by using your distributive property or FOIL. Some of you may have learned to use FOIL. You may have also remembered that you had a special product that x minus y times x plus y, we called these conjugates, always turned out to be x squared minus y squared. Well, that same property is going to apply here. If we went through and did our multiplication, we're going to have 1 squared, which is 1, minus tangent squared. If you're not sure, then you go through and do all of FOIL. 1 times 1 is the 1. Then 1 times negative tangent was negative tangent. Tangent times 1 was positive tangent, and those subtracted out. And then you have minus your tangent squared. Now again, anytime I see a 1 and a function squared, I always go back and I think, well, my Pythagorean identities. So if we went back and we looked at those, we have our Pythagorean identity, which actually says 1 plus tangent squared equals secant squared. Well, there's no way to make a 1 plus tangent squared 1 minus tangent squared. So here we can't do any more simplifying. That would be our final answer. If we wanted to multiply cosine theta plus sine theta squared. Again, this looks like a binomial squared, like x plus y squared. Some of you learned a property that when you multiply, when you have square a binomial, x plus y squared, you learned that that was the first term squared, then the same sign, and it was twice that product, plus the last term squared. And if you did, that's fine to do. That will still apply here. If you didn't learn that pattern, then all you have to do is write it down twice. Cosine theta plus sine theta times cosine theta plus sine theta. That's what it means to square it. And go through and use your distributive property or FOIL. So you would have cosine squared plus cosine times sine plus sine times cosine plus sine squared. So this would give you cosine squared plus, well, these are actually the same because of the commutative property, so that would be 2 sine theta cosine theta plus sine squared theta. Well, when we stop to look at this, we might notice, and we can use our commutative property anytime we want, but we have a cosine squared plus sine squared. Well, we have an identity that says cosine squared plus sine squared is 1. So this would be 1 plus 2 sine theta cosine theta. And we have it, we've done our multiplication and have it simplified down. Okay, let's look at this problem. And again, what we're doing in this section is learning how to do our operations on our trigonometric expressions, how to add and multiply uh, and subtract. And then we're going, right here, we're going to look at some problems with radicals. And they all go back to the same principles that we learned with our numbers and with our variables, complex numbers with radicals that we've learned in algebra. Here we have a problem that it says to simplify the square root of x squared plus 4 as much as possible after substituting 2 tangent theta for x. Well, let's see what we would end up doing here. If we substitute in, we would have the square root, and in place of x, we're going to put 2 tangent theta plus 4. Now here we have a product that we're squaring. We know that from algebra we have a property that says if you raise a product to a power, you raise each one of them to that power. It's one of our exponent rules. So we're going to have to raise the powers first. You always have to do all the simplification before you can do the square root. So that would give us 4 tangent squared theta plus 4. Now, you can never simplify a radical while it has a plus sign. We have to have factors. It has to be a multiplication problem here before we can do any simplification. So if we notice, we have a common factor of 4. So let's write this in factored form of 4 times tangent squared theta plus 1. So now we have a multiplication problem and factors, and we can do our simplification. But if you notice right there, tangent squared theta plus 1 was secant squared. That was one of our Pythagorean identities. And what we've learned with our radicals is when you have a product that you're taking a square root of, you take the square root of each one of them. So the square root of 4 is 2. The square root of secant squared is secant. Now, technically, we should put that in absolute values to make sure that that value is positive. We always want the principal root. So now we've simplified it down. But you need to remember that with radicals, you can only take roots of factors, not of add-ins. So we could not take the root here at this stage. Let's do another one of these. So let's take the expression the square root of x squared plus 4. We want to simplify this as much as possible. Oops, let me change that. That was the same as what we had. X squared minus 36. Let's do a different one. And we're going to do this after we've substituted in 6 secant theta for x. So as we substitute in 6 secant theta, and again, most of this is just to remind you how you do work with radicals and see that we end up doing the same thing with our trigonometric. Here we have a product being squared, so we're going to square each one. So that would be 36 secant squared minus 36. Now we cannot take the root of it while it's a subtraction problem. It has to be a multiplication problem. But we notice we have a common factor of 36. So we factor that out, and have secant squared theta minus 1. Well, we know that 1 plus tangent squared equals secant squared. So let's just write that down. We have 1 plus tangent squared equals secant squared. That's a Pythagorean identity. So if we subtract 1 from both sides, tangent squared equals secant squared minus 1. So we could replace our secant squared minus 1 with tangent squared. And now we can take the square root because they're factors. So the square root of 36 is 6. The square root of tangent squared is tangent. And again, that should be in absolute values. So we've looked at how to add, subtract, multiply, and how to simplify our radical expressions with our trigonometric problems. Now, one last thing that we want to look at here, and this is just a few problems that are fairly simple to prepare you for some identities that we will be proving later. And this is called proving an identity. So we're going to be given an expression that says that the cosine of theta times the tangent of theta is equal to the sine of theta. Now remember, an identity is something that's true for every value of theta. This isn't an identity that you need to memorize. But if you were given this, we want to prove that it is always true, no matter what your angles are. The way that we do this proof, this is called a T-proof. We're going to draw a T down right here, a line down here. And we're going to take the left-hand side, which is a little bit more complicated, and only by substituting in identities or doing addition and subtraction, we're going to get it down to where the last word here is sine theta. Now, we're not going to do anything over on this side. This isn't working with an equation. This isn't solving. We're not going to add the same thing to both sides like we would in solving the equation. We're just going to work strictly with one side. Now, often the easy way to start is to write everything in terms of sine and cosine. So we have cosine theta here. We know that tangent is sine theta over cosine theta. So we just replace tangent. We don't have to put equal sign. We know that what we have here, here's still our cosine. We've replaced tangent with sine over cosine because that's an identity. Now, if we did our multiplication, we know we have a common factor there, so we can cancel, and we end up with sine over 1, which is sine theta. So our last line here, sine theta, is the same as this. We've proven that this is true by substituting in our identities. And that's called proving an identity or verifying an identity. It's kind of like working puzzles. You're looking for values that would make it that you can substitute in. Okay, let's take this one. The cosecant theta times tangent theta divided by secant theta equals 1. So again, we're going to do our T-proof. We're only going to work on this side. And some of you may start one way, some of you may start another way. As long as you prove it by substituting in your identities or just doing computations, then it's okay. So I'm going to start out that cosecant is 1 over sine times tangent, which is sine over cosine. And that's all over secant, and I know that secant is 1 over cosine. Well, if I look at my numerator, we want to simplify our numerator, I can cancel my sines, and I've ended up with 1 over cosine over 1 over cosine. And we know that anything divided by itself is 1. So that would work out. Let me show you just another way if we'd approached it a little differently. let's take that same one, cosecant theta times tangent theta, and then it's divided by secant, which is the same as times 1 over secant, and I'm not writing the whole thing down to begin with. I'm just going through what I could have done on this side. And 1 over secant is cosine. So we could have said, well, this is cosecant is 1 over sine. Tangent is cosine over sine. And 1 over secant is cosine. Now, I put that tangent wrong. I know you're yelling at me, saying that was cotangent. Tangent is sine over cosine. And now our sines cancel, our cosines cancel, and we were left with 1. So it's just a little different approach. It's kind of how you look at it and how you see it. Again, we're not saying there's only one way to get there. There's several ways, and each route, as long as each step is an acceptable step, then it's okay. If we have secant theta times cotangent theta minus sine theta equals cosine squared over sine theta. We want to verify this. And we're going to work with the left-hand side, so we're not going to do anything over here. All that we're going to do is here. And again, since we want it in terms of sine and cosine, that's how I would start. Secant is 1 over cosine. Cotangent is cosine over sine minus sine. Well, this is real nice. We can cancel these cosines, so we have 1 over sine theta minus sine theta. Now, this is a subtraction problem. To do subtraction, you need a common denominator. So it's going to be sine theta because this is over 1. So we have to multiply our denominator by sine theta, so we multiply our numerator, and we have 1 minus sine squared theta over sine theta. And 1 minus sine squared theta is cosine squared theta. That's using that Pythagorean identity that sine squared plus cosine squared is 1. So 1 minus sine squared is cosine squared. And so we verified that for this identity right up here, it's going to be true for all values of theta. Okay, we have one last one. Secant theta times sine theta plus cosine theta equals tangent theta plus 1. All right, we've got and I don't know that it's necessary that you draw the T, but it's always helpful to me because that's a reminder. I never cross this line. I'm only going to work with this side, and I'm not going to cross the line. I'm not going to do anything over here. Now what we have here is a multiplication problem. So we can use our distributive property, and we could have secant theta times sine theta plus secant theta times cosine theta. Well, it's a little bit hard to work with this, so let's write secant as 1 over cosine times sine. And right here, secant and cosine are reciprocals. You could write secant as 1 over cosine, but we know that they're reciprocals, and anytime you multiply reciprocals, you get 1. So what we have is sine theta over cosine theta, just doing this multiplication, 1 times sine, cosine times 1, plus 1, and sine over cosine is tangent theta. And so there we have what we ended up with on our left-hand side is the same as what we have on our right-hand side. And these are some proofs that we're verifying to show that they're true for every value. But again, it's things where we're substituting in those identities. So make sure that you have memorized those fundamental identities.